Hi, I'm Wendy Zuckerman and you're listening to Science Versus from Gimlet Media. This is the third episode in our week-long series focused on big election issues. Today's episode, climate change. Since his presidential campaign, Donald Trump has been a climate change skeptic.
Who believes in global warming?
All of this with the global warming and that, a lot of it's a hoax. It's a hoax. I mean, it's a money-making industry, okay? It's a hoax.
And even though he recently kind of acknowledged climate change, so far in his presidency, we've seen a lot of things that made climate scientists nervous. Information about climate change and renewable energy has been scrubbed from government websites. President Trump signed an executive order making it easier to produce fossil fuels like coal and natural gas. And of course, he pulled out of the Paris Climate Agreement. And Trump says, basically, we don't know for sure if the changes we're seeing to our planet are because of climate change that was caused by humans.
You don't know whether or not that would have happened with or without man. You don't know.
What about the scientists who say it's worse than ever?
You'd have to show me the scientists.
Show me the scientists? Okay. But the truth is, while it's easy to dismiss climate change deniers, there were times when scientists weren't sure what was going on here. It took years to uncover it. And that's what we're talking about today. This episode was originally published last year, and we've updated it with new science. So here it is, science versus climate change. Yep, we're pitting facts against our future.
Got ocean all around us. We can look down and see little...
Is that a dolphin?
Oh, that was a little dolphin, yeah.
Oh, whoa!
Surprisingly small, though. I wonder what that was.
I'm walking on a pier in San Diego, California with Ralph Keeling. He's a professor at Scripps Institution of Oceanography. Oh, and look at the school of fishes.
The dolphins went right by them. They must not be hungry.
Maybe they felt bad interrupting them while they were at school.
I can't touch that.
Yep, just two nerds hanging out. Ralph has taken me out on the pier to do something that his family has been doing for decades. Collecting air samples. You see, Ralph's dad was a scientist too. His name was David Keeling, and David took the very first precise measurements of carbon dioxide in the atmosphere. Ralph tells me the air has to be pretty damn clean to get a good reading. So that's why we're out on the pier, to get as far away from traffic as possible. We even have to hold our breath when taking the sample, because when humans breathe, we breathe out carbon dioxide.
You wait until you're ready to take a sample, and then you hold your breath, and you walk into the wind.
Ralph whips out something that looks like a glass balloon. All the air has already been sucked out of it, so it creates a vacuum inside. And when Ralph carefully opens the vessel, air gets sucked in.
Now I close it off, and we have an air sample.
It's cool because you can't see it, and then it just makes these noises as to show this is a vacuum. And
that's one of the amazing things about this work is that it's really Mother Nature speaking through what you're doing, and you're actually tapping into it.
Back in the 1950s, when Ralph's father started taking these carbon dioxide measurements, he learned a lot from Mother Nature. In fact, those measurements helped create a new field of climate science and changed our understanding of the world in ways that we're still grappling with today. You see, when it comes to climate change, many of us still have doubts. A recent Pew survey found that only about half of Americans think that climate change is caused by humans, and the rest say it's either the result of natural causes or there's no evidence for it at all. Yet, at least 97% of climate scientists agree that it is extremely likely that climate change is caused by human activities. So on today's show, we're going to go all the way back to the beginning of climate science, to when Ralph's father first started taking his measurements. And we're going to ask, how are scientists so sure that carbon dioxide is warming the world? And why do they think that humans are to blame? Then we're going to look into the climate change crystal ball to try to figure out, what is this warming going to do to our planet? When it comes to climate change, there are lots of opinions. But then there's science. Science versus climate change is coming up just after the break. Welcome back. We're starting our story of climate change in the 1950s when Ralph Keeling was just a kid and he used to go visit his father in his lab, and Ralph still remembers what it looked like.
Had all these glass tubes and pumps whirring, and there was a cartoon on television called Felix the Cat, who had this sort of mad scientist guy, Poindexter, who also had glassware that would occasionally blow up on him. My exposure to science consisted of that cartoon on television in my father's lab, and they were very concordant.
Let's go to the laboratory.
Now, while Felix the Cat was running in the background, the elder Keeling was working on this experiment that had nothing to do with climate science at first. Ralph's father was researching rocks, but for that project, he had to know how much carbon dioxide was in the air. And this was a problem, because at the time, there was no way to precisely measure carbon dioxide in the atmosphere. So he had to invent something. And he did. A machine. Those were the noisy pumps that Ralph remembers. And this machine was a breakthrough, because before that, we could only get really rough estimates of how much carbon dioxide was in the atmosphere. But Ralph's dad's machine, it was the first that could very precisely measure how much CO2 was in the air. It could measure carbon dioxide down to parts per million.
What is parts per million? What does that actually mean?
So, yeah, if you have a million molecules of air, it means that out of those million, 315 are carbon dioxide molecules.
It's a tiny percentage.
Well, it's small, but sometimes things that are in small abundance matter.
And Ralph's dad, David, was just about to find out how important small things could be. In 1958, David's first measurement showed that there were around 313 parts per million of carbon dioxide in the atmosphere. But he soon noticed that CO2 levels were creeping up and up and up. In 1969, a decade after he first started tracking it, he noted that carbon dioxide was up by 8 parts per million. David knew this was no anomaly. He later described it as unmistakable. And this was because he wasn't just going on one measurement. He helped set up instruments in other sites around the world. Hawaii, Alaska, New Zealand, the South Pole, and even over the Pacific Ocean. Some pilots were recruited to capture air samples during Air Force recon flights. By the mid-1970s, the fact that carbon dioxide was going up was a scientific certainty. But that doesn't mean it felt like a big deal. Some of David's colleagues even thought that he should stop measuring it.
I think a lot of his colleagues thought, oh, you're nuts to keep that going.
But David, he did keep going. He didn't know exactly what the increasing numbers would mean for the world, but he felt that the change he was seeing was important and something worth keeping track of.
And so he realized that his work had a different kind of importance, because if he abandoned it, humanity would not know what was happening right now, and that ought to matter.
And then, in the late 1970s, scientists noticed another change. Teams all around the world saw that the average global surface temperature was rising too. Temperatures in the 1970s were about 0.5 degrees Celsius or 0.9 Fahrenheit warmer than almost 100 years before. And so, to explain it, scientists, including David Keeling, dug up this 100-year-old theory. You see, in the late 1800s, a Swedish chemist named Svante Arrhenius knew that carbon dioxide could absorb heat from the sun. So he calculated that if we had more and more carbon dioxide, say by burning fossil fuels, it would absorb more and more heat, ultimately trapping heat inside the Earth's atmosphere and acting kind of like a blanket over our planet. But while a few scientists had pursued that theory back at the turn of the century, it hadn't really taken off. And that was pretty much because no one could measure carbon dioxide precisely enough to recognise the changes that were happening. That was until David Keeling invented that machine. But once David's data was out there, then his colleagues started thinking. Take this theory that Svante had, combine it with David's undeniable findings, and it was possible to explain why the world was getting warmer. Because of carbon. But there wasn't scientific consensus. In fact, a big National Academy of Sciences report written in 1983 said that while carbon dioxide was a compelling theory as to explain why the world might be warming, it was not yet confirmed as the culprit. Why? Because there were other suspects around. So, what were those other suspects? One of them was pretty explosive. Volcanoes. Some scientists thought that perhaps there hadn't been as many volcanic eruptions recently. Volcanic eruptions inject a whole bunch of junk into the stratosphere, ash, dust and sulfur dioxide. And this stuff reflects sunlight away from the Earth. It can, in fact, cool parts of the world down. In the 18th century, a volcano erupted in northern Europe for 8 months, leaving the northern hemisphere about 1 degree Celsius colder than usual. So, some of those scientists noticing warming in the 1970s thought maybe fewer volcanoes were erupting and that was warming the world. To test this out, scientists looked through historical data and found that in the second half of the century, there actually were a bunch of eruptions in Mexico, the Philippines, and even more recently, in 2010, a volcano in Iceland spewed ash into the air for more than 5 weeks. Do you remember this one? It caused havoc to air traffic as well as reporters who couldn't pronounce it.
The glacier is called Eyjafjallajökull.
Eyjafjallajökull. Just think of, hey, you forgot your yogurt.
No, I've got it. So in 2010, the Eyjafjallajökull volcano spewed ash and dust in the air like other volcanoes recently. So, the number of eruptions hadn't changed on average, but the temperature of the world kept going up. So, scientists moved on. Some tried to find other explanations, pinning it on changes in how the Earth spins around the sun. Because the Earth can orbit just a touch closer or further away from the sun, sending our climate into a flux. Or perhaps it was changes in the sun's activity that was explaining this change in temperature. But the sun tends to power up and down in 11-year cycles, and the Earth's orbit changes over hundreds of thousands of years. They just didn't line up with the trends that scientists were seeing. So these were all ruled out too. Really, the big thing they kept turning back to was what that Swedish guy had said more than 100 years ago, that carbon dioxide was trapping heat from the sun and warming the world. And Ralph Keeling reckons that it's kind of incredible that this theoretical prediction from 100 years ago lines up with what we're actually seeing today.
It's a triumph of science. It doesn't feel like a triumph for humanity, but it was a triumph for science.
Back in Ralph's office, he showed me all the measurements that he and his dad have made.
So you're looking at carbon dioxide starting in 1950.
Almost 60 years of samples. And it's a graph with one line going up. And it's now called the Keeling curve.
315 parts per million, and they rise up to the right to something around 405 parts per million.
405 parts per million. So that's up 92 parts per million from when the Keelings first started measuring CO2. And when it comes to warming, the last 3 decades have each successively been the warmest decade at the Earth's surface since 1850. Okay, so thanks to the Keeling's work, we know that carbon dioxide is rising. We know that it's warming the world. But those facts alone don't mean that humans are responsible. So, how did science reach that conclusion? The thing is that carbon dioxide doesn't just come from burning fossil fuels. It's all around us. It's in the atmosphere. Humans breathe it out, and plants absorb it when they grow. The oceans soak up and release carbon dioxide. In many ways, the planet is kind of constantly breathing in and out carbon dioxide. But carbon dioxide is also pumped out when we burn fossil fuels like coal, oil, and natural gas. So, to find out whether more carbon dioxide in the atmosphere was from the planet breathing or fossil fuels or something else, we have to investigate the carbon dioxide measurements that the Keelings and others have made. And this is something that Chris Field, a professor of environmental studies and director of the Stanford Woods Institute in California, told us all about.
And the scientists kind of act like detectives. They use a variety of techniques, like on CSI.
When was the last time you watched CSI?
Oh, I don't know. Is CSI even still on?
He's probably more into The Good Wife. And Chris has been studying the secrets of carbon dioxide for decades. And so how can we track what is carbon dioxide that's being farted out of trees and animals, and what is carbon dioxide that's coming from fossil fuels?
It's really pretty easy. And I need to do a little mini chemistry lesson to help make this clear. But
Wowee.
you can think about several flavors of carbon dioxide.
Chris basically tells us that there are different types of carbon out there. And this may sound surprising, but there's carbon that's not radioactive and carbon that is radioactive. Radioactive carbon disappears over a very, very long period of time. Now, anything on the Earth's surface with carbon in it has both kinds of carbon. It's got the radioactive kind and the non-radioactive kind. So, yes, you and me, we're all a little bit radioactive. And so are all the plants and the animals that you see around you. But there's something that has practically no radioactive carbon in it, and that's fossil fuels. Why? Because fossil fuels are made of dead animals and plants that have been buried for millions of years. And during that time, the radioactive carbon inside them slowly disappears. So after millions of years, it's pretty much gone. So when we burn oil and gas and coal today, they basically don't have radioactive carbon left in them, just that other kind of carbon. So when scientists like Ralph measure samples of air, they find lots of carbon that doesn't have any radioactivity, meaning it's carbon that's been smushed beneath the Earth's surface for millions of years.
Of the human-released CO2, because it doesn't have any of this radioactivity. When Keeling started his measurements, we could tell really, really clearly, and we'd see the signal.
And that's how scientists know whether carbon in the air is from burning fossil fuels or from the planet breathing.
And that signal is really very, very clear.
Using these measurements and other studies, the Intergovernmental Panel on Climate Change, or the IPCC, announced in 2014 that there was enough evidence to say that it was extremely likely that the burning of fossil fuels was the main cause of climate change in the mid-20th century. And by the way, they also wrote that it's not just carbon dioxide causing all this trouble. There are other greenhouse gases, such as methane, which partly comes from cows belching, and nitrous oxides, as well as water vapour. And Chris says that if there was a big problem with this conclusion, at this point, we would know, because scientists have been trying to poke holes in it for years.
So every scientist out there is banging on this infrastructure of knowledge as hard as he or she can to find what's wrong with it. And nobody's found a flaw. Everybody fine-tunes, but everybody's trying to find that big flaw that would make him or her famous.
So, this is why 97% or more of climate scientists agree that warming trends are caused by human activities. But just because most of science can agree on that point doesn't mean the experts have it all figured out. Because there's still a lot of disagreement about what comes next. What will all of this warming mean for our future? And this disagreement is happening right up close. Right at Ralph Keeling's lab, in fact.
Oh, there's Steve. This is Wendy.
Hey.
How are you? She's a mobile reporting unit.
Very cool.
This is Dr. Steve Piper, a specialist in geochemistry at Scripps Institution of Oceanography. And he's been working alongside Ralph and his dad for decades.
That's right.
Very distinguished scientist.
I started with the first Keeling, and now I'm on the second Keeling. A whole career with the Keelings.
And what did you think about that trend line that kept going up and up? Were you worried?
No, not particularly. I tend to be one that thinks there's some way around every problem. I don't like to jump on the bandwagon.
What's the bandwagon?
Well, you're going to really nail me on it, aren't you? Well, the bandwagon to me is like, it's going to be a total catastrophe. I tend to be more of a skeptic.
When you say a skeptic.
I must say, so there's no question that CO2 is increasing and it's caused by man. And we can show it's well correlated with fossil fuel consumption. So then the next question is temperature increasing? It's well established that the surface air temperature is increasing. I mean, there are still questions about what the real dangerous impacts are going to be of the change, I think.
In other words, maybe we shouldn't be so worried. But some people, they are worried. We'll tell you how worried you should be after the break. Welcome back. Okay, so carbon dioxide in the atmosphere is going up, and that's mainly due to burning fossil fuels. That gas is trapping heat and warming our planet. And what we haven't talked about yet is the many, many changes that scientists are seeing all around the world. So let's take a trip around this planet of ours to see what this heating and carbon dioxide is doing.
I'm Blair Truan. I'm a senior climatologist with the Australian Bureau of Meteorology.
Hi, I'm Jane Hill. I'm a professor of ecology at York in the UK.
I'm Regent Bhaktakashta. I work in the Kathmandu University in Nepal.
Well, my name is Mark Serez, and I'm an Arctic climate scientist.
I'm Marcia Macedo. I work in the southeastern Brazilian Amazon. We've seen more intense wildfires, and we've seen forests that previously wouldn't burn more than once every 500 years, burn several times in a decade.
2013, 14 and 15 were the three warmest springs on record for Australia.
So on average, butterflies in the UK are shifting northwards by about 2 kilometres a year.
I'm in the Fiji Islands. The change in seawater temperature is very profound effects on the coral bleaching.
In the case of Himalayan glaciers in Nepal now, we are seeing that the glaciers are becoming smaller and smaller.
Back in the 1980s, in, say, late August, early September, the Arctic Ocean was white. White because it was covered with sea ice. And if you look at it today, it's so different. It's mostly a blue ocean now.
So, climate change is happening right now. It's changing the way that butterflies and many other animals, in fact, are migrating. It's changing how many days of extreme weather we're having. And while it's still very difficult for scientists to pinpoint whether any single event that we see is caused by climate change or would have happened with natural variation, the trends that we see already suggest that climate change is reshaping our planet, here and now. And it's threatening the homes of hundreds of thousands of people. So that's what's happening now. And this is still a big open question. That is, what does happen next? What will all of this warming and carbon do to our planet in the future? Will winter turn into summer? Will sea levels rise enough to take out whole countries? Will weather patterns change so drastically that croplands turn into deserts? Will this happen?
Every New York City neighborhood you'll see in this video will be underwater if we don't stop climate change.
How much time do we have? How much time does the human race have?
I can't imagine there will be a human on the planet in 10 years.
Whoa, 10 years? Will we even have time to do science versus that little guy in the refrigerator? How does the light turn on and off? So much to do. Okay, so there's no credible evidence that we'll all be dead in 10 years. But there are real questions about what the world will look like in 100 or 200 years. To sort through those questions, we're now going to meet someone whose job it is to predict the future. In order to find David Pearce, I'm walking on Downwind Way, which is funny because it sounds like a fart. David.
Hey.
Hello. David Pearce is also at Scripps. He's just across the road from Ralph Keeling. You counted on your website your research interests as total world domination via long-range climate predictions. Just wondering how that was going so far.
Probably about 5% accomplished. No, it's yeah. So I think you have to keep a sense of humor in climate research because sometimes you feel like there's a buzzard of doom sitting on everyone's shoulder.
So what is David doing that has turned him into a buzzard of doom? David is a climate modeller, which means he's gaming out our future using climate models. A climate model is a computer-generated simulation of all the major processes that drive our climate. This is heat coming from the sun, winds moving that heat around, greenhouse gases trapping that heat, oceans absorbing that heat. They even include how water gets around in all its various forms: ice, rain, and water vapour. And what gets plugged into the models are real observations that we've made about the climate, like those measurements from the Keelings, as well as temperature gauges, satellite data, and even information that we can squeeze out of ice cores, which is very old ice. So combining our understanding of how climate processes work along with our real data, the model will spit out a prediction of what the future will hold, say if we stop using fossil fuels today or if we keep burning fossil fuels the way we do now. When you hear a climate change prediction about our future, chances are it came from these climate models. And there are more than 40 different climate models made from teams around the world. All these models are based on the same basic ideas about what drives climate change, but they crunch their numbers in slightly different ways. To see how good the models are, scientists can start the model at the very beginning of the 20th century and run them to make sure they accurately simulate the changes to our climate that we've already seen. And they more or less do. Do you have a model up on your screen that we can have a look at?
And I just have a few of them here. But let's look at one. This is, actually, you're from Australia. Let's go to the Australian model.
Sure. No, David isn't hacking into the mainframe here. He's actually pulling up one climate model made by Australian scientists. A map of the world pops up on his screen, and it's pretty pixelated. It looks a bit like a 90s video game. And each of these pixels represents a patch of the ocean or land that's the size of Connecticut.
So this model has been run starting probably in about 1850 to 1880, but then it goes all the way through year 2100. So we can see what could happen in the future.
Okay, so first up, I wanted to use these models to see how temperature will change in the future. I wanted to know what would happen if we just keep burning fossil fuels the way we are now. So David pulls up a map of the world in the 19th century. The map is colour-coded. There's red bits where it's warm, like the Australian desert, while the Arctic is blue. And then David runs the model to 2100.
And then there's a slow trend such that overall things get somewhat warmer.
The screen gets redder. It shows a world that is around 4.5 degrees Celsius warmer than today. That's around 8 Fahrenheit. But of course, this is just one model. When you look at more than 40 models, which is what the IPCC does, the models differ slightly in their predictions by about 1 degree Celsius in either direction.
So it's not like winter will turn into summer, but an extra 5 Celsius on top of summer is a lot, and that's on average. What we consider to be a historically warm July now will be distinctly on the cold side for an average July by about 2060.
In fact, 5 degrees is an average, which means it includes the temperature over the ocean, which tends to be cooler than the rest of the planet. And David says this will likely mean more extreme weather events.
Heat waves are going to be worse, downpours are going to be worse, flooding is going to be worse, droughts are going to be worse. I mean, it's the extremes where you really see the biggest expression of climate change.
And to put this into perspective, when we look far, far back into our planet's history, when the temperature dropped by 5 degrees Celsius, it was the difference between being in an ice age and not. So, when it comes to predicting the temperature in the future, the models are pretty unanimous. They all predict a very similar world. We can say with a lot of certainty that if we keep living the way we are now, temperatures will rise by 3 to 5 degrees Celsius by the end of the century. But what is harder to model is what will that temperature bump mean for, say, sea level rise?
How high will it get?
I think that's an area in active research.
An area of active research. That's kind of scientist speak for... Now, to be clear, this is not the kind of you do when someone asks you, what's the capital of Burundi? Which is Bujumbura, by the way. It means that scientists are actively studying this, but acknowledging that there are gaps in what they know. Still, for brevity, we're just going to call these uncertainties. Now, it's not all when it comes to sea level rising. We know the basic reasons why sea levels rise, including that water expands when it heats and that ice sheets melt, trickling water into the ocean. In fact, recently, the glaciers and ice sheets have been melting by an average of 549 gigatons each year. We also know how much sea levels have risen in the past 25 years or so. Since 1993, global sea levels have gone up by 3 inches. But what we don't know is how quickly they will rise in the future. And one reason we don't know this is because we can't accurately predict one of the causes of sea level rise: how exactly the ice sheets will melt. Because these ice sheets don't melt predictably like ice on a sidewalk. It's not all one slow melt. One of the ways that these big boys lose mass is when huge chunks of ice crack. Once a crack forms, melting water can pour into it and bust its way down, eventually breaking that cracked off ice and sending it into the ocean. This is the sound of a big chunk of ice breaking apart from Greenland. And when we say big, we mean big. In 2013, an iceberg the size of Singapore that went by the alias B31 broke loose from Antarctica. As it struck out into the water, its surface area increased, exposing it to more heat and causing it to melt faster. But it's hard to know how often this has happened and whether it's been happening more often recently. We reached out to a couple of glaciologists to find out, and they told us that part of the problem is that we've only been properly monitoring them since the 1970s. But while there isn't great data on that, here's some good news. We got a really great voicemail from one of the glaciologists. His name is Jason Box.
Have a nice day. Or as I like to say, have an ice day.
Just 2 nerds hanging out. Anyway, the point is we don't know how much ice has broken off these big boys in the past century, and so it's actually very difficult to predict how and when the cracks will form in the future. Here's David again.
And if big pieces of the glaciers start falling off Antarctica, basically, you can get a very rapid rise in sea level. And you actually, to me...
But what's the chance of that really happening in, say, the next 100 years?
I would say no one knows exactly what those chances are. I mean, it's enough to be thinking about and concerned about, but I think that's an area in active research.
In other words... And these ice sheets are very important. Perhaps one of the worst-case scenarios was calculated in a paper published in 2016, and it predicted that in less than 500 years, we could have a 15-metre sea level rise. That's almost 50 feet. That would mean saying goodbye to Miami, Shanghai, and half of Brooklyn. It means in 500 years, we'd have lost whole countries. Bangladesh and the Netherlands, gone. That prediction was just from one paper, though. The most recent IPCC report ultimately said that our understanding here was so limited that they couldn't make conclusions on how much the sea level would rise due to melting ice sheets. So when it comes to predicting sea level rise, there's a lot we don't know. It's going up, but how quickly it will rise and by how much, that's an area of active research. So, and then there are other things that scientists know even less about, like how climate change will affect the currents moving around our ocean and what that means for us. There's this one big conveyor belt of water which chugs around the world. It comes up from the tropics, whooshing past the east coast of the United States and then shooting up to Iceland and Greenland.
Well, it's called the Atlantic Meridional Overturning Circulation, or AMOC.
AMOC, amok.
Yes, it's gone amok.
The AMOC. Many Americans know one part of it as the Gulf Stream, and it's important because it transports warm water around the world, particularly from the tropics up to Europe, giving Europe its relatively warm winters. The AMOC's driving force is partly set by how salty the water is around it. And with that melting ice we just talked about pouring fresh water into the salty oceans, it could slow the AMOC down. And it's believed that if the AMOC collapsed completely, thanks to a warming planet, it could affect weather patterns around the world, with drastic impacts on agriculture. It's thought that in the past, when the AMOC did start slowing down, it got really cold in parts of the world.
In fact, there is a very bad movie about this, I think called The Day After Tomorrow, where the theory there was that the AMOC would suddenly stop, and so Northern Europe and so on would instantly freeze. And I think it had some great pictures of people running down the street, freezing in their tracks. Happily, the real climate does not work that quickly.
Headland had some pretty convincing data. They've asked me to feed it into my paleoclimate model to track the next set of events. I think we're on the verge of a major climate shift.
Getting back to the real science, though, there's a lot of uncertainty here. A 2016 paper that looked at almost 500 studies on the AMOC said that we needed more data to accurately model it. They ultimately concluded that the best climate models we have do not predict that the AMOC will collapse. But they did say it would probably slow down. Ultimately, David says,
that's an area in active research.
So you can count the AMOC as another... Yes, like the ice sheets, we simply don't have enough data to know exactly how the AMOC is working or how to model it in the future. According to the National Oceanic and Atmospheric Administration, or NOAA, we would need to have been keeping track of it for, quote, decades to properly characterise and monitor the AMOC, end quote. Amidst all of these what have we learnt? When it comes to climate change, yes, there are uncertainties, like how high sea levels will rise by the end of the century and how slow the AMOC will get. But there are also certainties, things that scientists have worked out, like that carbon dioxide is rising, that we, humans, did it, and that it's causing the average temperature of our planet to rise. If we keep living the way we are now, all climate models show that temperatures will keep rising. And what we're seeing around the world right now, it is part of a predicted trend. Just before Ralph Keeling took his samples back to the lab, I asked him,
do you ever get a bit philosophical about looking out the horizon?
Well, yeah, I don't need to be looking at the horizon to get philosophical. I mean, I guess the point when I get philosophical is when I'm with my children. the world they live in is changing fast, and some of the things they are growing up with and are seeing now will be gone when they're grown.
Things like which things?
Well, like you could see that a town up in the mountains here, the trees are dying. And you can see that trees further down the slope have been dying. We can't possibly pretend that we're going to be preserving the world in a way that's pristine. It would be nice to do that, but we're way too far into this to pretend that we're not going to have profound changes on the planet happening.
Hang on a second. Our future is not set in stone. And this takes us to the final uncertainty that we have to talk about. And it's the biggest uncertainty of all, in fact. And that is, what will humans do next? David Pearce, our buzzard of doom, says that when you look at the climate models, the biggest uncertainty in how fast our world will warm is our actions. Like how much carbon dioxide we choose to keep emitting.
So the biggest source of uncertainty by the end of the century is what we do as a society. So you see, it's a funny way of thinking about uncertainty. People might say it's uncertain what I will eat on Friday, but I determine what I'm going to eat on Friday. So to me, it seems like a very weird definition of uncertainty because we're controlling it. We're controlling the major source of uncertainty by our actions.
Amidst all this, then, let's leave the final words to one of the greatest philosophers of our time, Captain Planet.
The power is yours.
Oh, and just to be clear, by the power is yours, the yours is obviously the most powerful governments in the world. Okay, cool. Thanks.
Captain Planet, he's our hero. Gonna take pollution.
Oh, and if they want to change things, they better move bloody fast. Just a few weeks ago, in October 2018, the IPCC released a new report saying we only have a few decades to drastically limit our carbon emissions to avoid climate change catastrophe. Okay, cool. Back to the music. But of course, it really would make a difference if everyone out there understood the science on climate change.
Magnified, and it's fighting on the planet side.
You'll pay for this, Captain Planet.
That's science versus climate change. Tomorrow, our final midterm election special. We're looking at the science of immigration. This episode has been produced by me, Wendy Zuckerman, and Dr. Diane Wu, with help from Shruti Ravindran and Heather Rogers. It's been updated by Meryl Horn. Our senior producer is Caitlin Sori, production assistance from Ben Kiebrick. We're edited by Annie Rose Strasser and Blythe Tyrrell. And a big thanks to Eric Mennel, Pat Walters, Caitlin Kenny, and Alex Bloomberg. Fact-checking by Michelle Harris, Ben Kiebrick, and Meryl Horn. Sound engineering, music production, and original scoring by Bobby Lord and Emma Munger. Even more thanks to Dr. Alexander Roble, Dr. Ted Scambos, Dr. Pieter Tans, Professor Jason Box, Associate Professor Zana Chase, Assistant Professor Martha Buckley, Sarah Shackleton, Stevie Lane, the Zuckerman family, and Joseph Lavelle Wilson. I'm Wendy Zuckerman. Back to you tomorrow.